start. Just to remind you where we are. So last week we have discussed about characterizing the needs of a building. Okay, so we have looked at the building and looked at how we can calculate the amount of heat that is needed so that we will be able afterwards to connect the energy system that satisfies the needs. And today, before going into looking at how we can satisfy the needs, I think it makes sense to first ask ourselves what are the options to reduce the amount of heat that is needed by the different buildings, so that we are including into our calculations the possibility to improve or to reduce the needs. Okay? So, and for doing this, I would like to start by giving you the word and asking you what would be, to your opinion, the options that the people have here to reduce the needs of the building. So what are the actions that we can take? So the floor is yours, so give me suggestions about how we can reduce the energy demands of buildings.
Isolation.
So you are going to isolate, so it means that you are going to add, I'm going to take just notes here, but that's correct, so we are going to decide insulate buildings. Other ideas?
You can use natural sunlight.
Yeah, how would you use the natural sunlight on an existing building?
We can use shading during lunchtime to reduce the cooling demand and not use shading during morning.
So smart operation in this case. So use of the shading systems. So let's add here. Smart operation. Yeah.
We can reduce the temperature of the house.
Yeah, and ask everyone to come with better shirts. Huh? Okay, yeah. Then or work harder, huh? Because it's also going to create more gains and reduce the heat demand. That's correct. Yeah. Other suggestions? Yeah.
If we increase the heat exchanger areas, we can reduce the supply temperature.
Reduce the supply temperature. Yeah. What would be the benefit of reducing the supply temperature?
We need to heat the supply temperature less, the supply for example, the heat exchanger here would be more efficient because it brings it has a smaller delta T.
So it would have so you would like to reduce the supply temperature. In fact, you do not have to increase the size of the radiators. So you have perhaps to just better use the radiators, because what the radiators are doing is that you have thermostats, okay, which are supposed to regulate the temperature. And if the temperature is too high, the valve is going to be closed. Okay? So it means that officially what you have to do to reduce the supply temperature is to optimize the supply temperature, so have a better knowledge of the radiators that are in the building, identify the one that has the lowest needed area, okay? So it means the valve that is always open, verify that it is always open, not because the room temperature is too high, but because the radiator is too small. Then you could then improve or increase the size of the radiator. Or if no one of the radiator is at the bottleneck, then you can reduce the temperature, okay, until you find one of the radiator being at the bottleneck. And the advantage of reducing the temperature, in fact, is an indirect advantage. And the indirect advantage is coming from the fact that we are heated with a heat pump. So if I'm reducing the temperature at which I have to supply the heat with the heat pump, it means that I'm going to reduce the amount of electricity that the heat pump is going to consume, meaning that I'm going to take more heat from the environment, right? So reducing the supply temperature is also a good idea. Other suggestions?
Maybe in support of smart operation, but we can reduce the for the interior for the night.
Yeah. So yeah, you're right. So here I'm going to add a T because it's the program of the comfort temperature. Okay. So it means that in reality we have to be sure that we are not heating the building when nobody's there. So for example, it would make sense to look at not heating the buildings in the weekend, for example, where there are less students in the classrooms, right? Other suggestions? Yeah. Yeah. So this is something which is at the level of the energy conversion system. So now I would like just to have still options for the reducing the needs. Yeah.
Using waste heat, recirculating waste heat.
Try to reuse the waste heat. That's correct. So I'm going to add here. Do you have an idea of where we will find waste heat? Here?
The ventilation. The ventilation.
And the ventilation? So what? So you consider that we have waste heat out of the ventilation?
Yes.
That's correct. Yeah. Which indeed means that we have to optimize the ventilation system. So to control the air, to be sure that we are not extracting too much, and to reduce the heat that is extracted, the heating value of the heat value of the air that is extracted out of the building. Other idea of where we can find the waste heat? Yeah.
Maybe when we use hot water in the sink. Or
Yeah. So the hot water is in fact related to waste heat. I must admit that in EPFL we have solved the problem. We have not anymore hot water in most of the tap systems. So because typically we do not need hot water in EPFL, but in most of the rooms of EPFL. Okay. But I do agree that as soon as we have showers, or if we have a kitchen, for example, where we have waste heat, where hot water, then it makes sense to reuse the waste heat of the hot water. Other idea?
maybe from the fridges.
Yeah, from the fridge, it's correct. So I would make a distinction between the normal fridge, which are typically heat in the house, the room directly, right? From the industrial one. And of course, if we are releasing the heat in the air heat exchanger on the roof, then it would make sense to reuse it directly. So I'm adding here refrigeration. Another idea? So in EPFL there is a heat source that is available, is the heat of computers. So we have big data centers here that supply you with the internet, with the backup, and with the virtual machines, etc. And all this, and with emails, and plus all the calculations, and all this power which is consumed in the data centers, in the computers, needs to be evacuated. So it's the first principle of thermodynamics. The system needs to be cooled down. And it's a heat source that can be used for heating purposes, right? So data centers that I'm going to add. Okay, so let's try to see what we can do with those options. I think that now the list is more or less complete. So I'm going to discuss how we are going to try to evaluate those options. So up to now you have ideas, okay? I say, okay, isolation, ventilation, etc. So now the problem is that we have to know what will be the impact of what we are going to do. It means that I need to update the value of the heat that is needed by the building on the different heating systems as a function of the decisions I'm going to take, right? So it means that now I need to make calculations. So for doing this, I'm going to look at what I was already doing last week, where I have written an energy balance of the building. And now what I have to do is to characterize flows. So it means that now I have to give values to the flow. So the flow of air, so the flow of air that is one here. So the flow of air that is extracted, for example, the heat that is radiated via the walls. So this is what is expressed here. So you have areas with different quality of isolation, which corresponds to a resistance to the heat transfer that I have to understand. I have here the comfort, which is in fact part of my model, okay? And once I have characterized the flows, I can identify where the, how the, so, there is a not great. Okay, so when I have to, as soon as I have characterized the flows by writing mass and energy balances, I will be able to know what is, for example, the amount of heat that is related to the flow of air that is coming from outside and that needs to be heated up to the temperature of the building. So what you have done last week was to characterize the terms on, or what you are doing during the exercise now, is to characterize the terms that defines the heat load that is here. And you are going to make this evaluation of the overall heat transfer coefficient that you have named the KTH, which is the sum of the contribution of air and the contribution of the deperdition via the walls. So if I have to improve the building efficiency, I'm going to start with improving the envelope. And there I will have a question to you. So let's assume that you have to calculate what will be the new heat demand if you increase the envelope. So what would you do? So you were suggesting to increase the insulation. So what would you do in order to say, okay, how can I quickly estimate what will be the new heat load that is needed?
I guess the information about the kind of insulation.
Yeah. This was the answer that I was expecting, with one difficulty there. Okay, because it's like asking the architect that he's going to ask to the civil engineer. So the problem is that you will need a lot of information for doing it. Okay, because you will need, in fact, to know what are the different options to increase for the isolating the envelope. Okay, and each option has quality, so a heat deperdition. And a different action, so you can add a new layer on the wall, you can change the windows. And the problem, and this is just a trick that I'm going to use here, the problem is that if we do this, then we will have a huge work to be done, okay? Without knowing if it really makes sense, so if I will win or reduce the heat load in a sufficient way. So what I would suggest to do instead is to use the norms. If you go into the Société des ingénieurs et architectes, so the Association for Engineers and Architects, they are giving you recommendations. Or there are some associations like Minergie, who is giving you target values, okay? And the state is also giving you target values. So what they say is that if you renovate a house, and if you want me to give you the authorization of doing it, then you have to reach a certain target. And this is something which is interesting because it allows you to have at least what you can expect. Okay, they are going to give you a minimum value that needs to be reached, and typically they give you also an order of magnitude of what will be the cost to reach it. Okay, it's an estimation, is a very rough estimation, but at least now what we can say is that, okay, let's assume that I'm going to transform my building, which has a given energy consumption that I have measured, into a Minergie building, and then I will know what is the expected amount of heat that needs to be released if I have done my job correctly. Okay? And this will be, let's say, an easy way of estimating what is going to happen. And I remind you that we have a lot of buildings to evaluate, and we have to take the decision about which one needs to be renovated and which one not. Okay? So it makes sense to have a first guess. And of course, as soon as we have decided to do it, so it means that with our approach, we have decided that the best would be to renovate building A, B, and C to reach my goals. Okay, then I will have to do the detailed engineering about how to reach the target that is set. Okay, but at least I will have an estimated value that I can use in order to go to make the calculation. So what I would propose is that you will look at on the internet, consult, for example, the Minergie.ch, okay, which is going to give you target values, and make the link between the target values, which are typically given in form of I'm going to be the one. The target values are typically given in kilowatt hour per square meter heated and per year. Okay, so this will be the value that will be given, okay? And I remind you that you have a model here, okay? And with this model, okay, what you can do is to calculate the integral over 1 year, so from January to December of the QBT, which is the amount of heat that is needed by the building, okay? Which will give you the kilowatt hour, and then you divide it by the square meter of the heated area of the building to obtain the value of QBT. Okay, so the amount of heat that is needed by the building. And then what you can do is to go back to the equation that you have here and deduce the heat transfer coefficient, or the heat depollution coefficient, sorry, of all the walls, so the sum of all the walls, that will allow you to reach the target. Okay? And by doing this, so here you will, I'm going to write it so that you have it. So for, no, sorry. You calculate the KL, which is the one that is in this formula here, in such a way the integral is equal to the target. And from there, you will deduce the amount of heat that is needed by the building with the distribution temperature it is connected to and the temperature at which, and the time at which the heat has to be supplied. So I will have the profile of the heat that is needed. Okay? Questions about this? So I summarize. You have a model which is calibrated, so you have just calculated the value which is here. And then what you do is that you say, okay, I'm going to improve the envelope in such a way that I'm going to reach a target. The target is given in kilowatt hour per square meter per year. And what I'm going to do is that I'm going to calculate the new heat deperdition coefficient, which is the new KL that is in the formula, in such a way that it reaches the target value. Now with the new one, I will have the new heating curve of the building, and I will be able to calculate the heat load that is needed by the building B on the distribution system D at any time, depending on the outside temperature, etc. Right? Meaning as well that now I will have two representations of the needs of the same building. Because the building will have two states, the non-renovated one and the renovated one. And I will have to decide, do I renovate it or not? Okay? And this I will do by optimization. And when I'm saying I'm doing it with optimization, it means that I will compare the benefit in the cost of supplying the heat with the investment that is needed in order to buy the insulation on the system. Okay? Is it clear? Okay? And as you are really creative, then you will say, well, I see more than one possible target. Because if you go to Minergie, for example, website, or if you go to the on the cantonal law as well, you will see that there is more than one target that can be reached. So you can be really ambitious or not really ambitious, or a little bit only, right? And you can therefore, by following the same approach, decide that the building can be in different states. For each of those states, you will have to invest more or less in isolation, for example, and you will have to then decide which one of the states is the most interesting to you. Okay? Questions about this part? No? It's clear? So in the calculations that we are asking to you, then what you will have to do is to make the calculations about the different states that you propose for each of the buildings that are considered. So isolation was the first the first idea for reducing the demand of a building. Okay. The second suggestion was to control the air. When I'm controlling the air, in fact, what do I do? And I'm not sure that it is the case here. If I'm looking, no. So it's an old building here, so we do not have an air regulation system here. But as soon as you have on a building an air regulation system, it means that you have a pipe, like the one that is here. You have a pipe, and in fact, on those pipes, as soon as you want to control the air, then you have to add a blower that is going to extract the air out of the building. Okay? And if you want to recover the heat of this, of the extracted air, you will have to add an exchanger. Okay? So it means that you will have a hot streams that will be cooled down, okay, from leaving the wall and then going into a heat exchanger to go outside to deliver the heat. But you need to find something to be heated towards the heat that you recover. And one of the options, you could also then decide that you exchange the heat directly with the radiators if you want. But you are not sure that there is a flow at the time where you extract the air. So one of the best way is to say, I'm going to preheat the air that is entering my room. Okay? Which has to enter the room. Because if I'm extracting air outside of this room here, if I do not add new air in the room, then the pressure is going to decrease. Okay? So what is typically happening in a building is that you extract the air out of the building, and at the same time there will be air that is going to enter the building. And the best would be to have a maximum of this air in a tube. So as soon as we enter a ventilation system, there will be two pipes. Okay? One pipe for the air extraction and another pipe for the air inlet. And if you have the two pipes, then what you can do is to, as soon as you extract the air, you create a reduction of pressure that is going to suck the air from outside, and the air is going to enter the room via the pipe that you have installed here. And then in between, you are going to install a heat exchanger that is going to preheat the air. So the air is going to go here, be preheated here by recovering the heat of the air that you extract out of the room. Okay. Unfortunately, the amount of air that is entering via the pipe is not the only air that is going to enter the room, because the room is not tight. So it means that you can see that there is a small section of passage below the door, for example, that is going to also let the air enter. So this is the infiltration air. So it means that the air that is going to enter via the pipe is always lower than the air that is extracted, because there are other flow of air that are entering because the building is not 100% tight. Okay, and so there are leakage. So in order to calculate the amount of air that the system needs, in fact, there is a trick. And the trick is, again, to look in the norms. People are saying that the amount of air that needs are giving you rules that says how much air needs to be replaced in a given volume per hour. Okay, which is a ventilation rate. So it is going to say that, for example, this room the total volume that is here needs to be replaced twice an hour. Okay? Now, if you know the volume of air, or it means if you know the volume of the building, okay? If you know the value of the air renewal rate, then you are able to calculate what is the flow of air that you have to extract, which gives you the flow of air that will be extracted. And the flow of air that is going to enter will be the flow of air that is extracted, so out here, plus, so this is the in, plus the air that is going to enter via infiltration. And typically we can define it as being a certain ratio of the air that is extracted. So let's say take 20% of the air that is extracted is coming directly from outside and not via the pipe. Okay? And then there will be, it means that now I have the flows, and if I want to calculate what will be the impact on the heat, the only thing that I will still need is to make an energy balance and to calculate what is the temperature that the air that is entering, so the one that is entering here, what is the temperature that will be reached. Okay? And for doing this, I'm going to make the calculation of a heat exchanger. Okay? So what I can do now is to look at the heat load of the heat exchanger, realizing that on the one hand, I have the hot stream that goes from the comfort temperature here to a certain value at the outlet of the heat exchanger. So this is the value of the heat exchanger here, right? And I'm going to preheat with this air another stream which has a lower flow because part is entering by infiltration, a lower flow that is at the temperature of the temperature at the external temperature, okay, and that will be heated up to a certain point, and the certain point is defined by is for sure lower than the temperature of the room, okay, and depends on the heat exchanger area that I'm going to buy. Okay, so it means that I can write the heat exchanger energy balance looking at the flow of air that is leaving, looking at the flow of air that is entering. The two heat loads needs to be the same because the heat exchanger is supposed to be adiabatic, so it means it is not releasing or radiating heat outside in the outside. It is mainly directly transferring heat from the hot stream to the cold stream, and I can calculate by applying the equation of the heat exchange, which is given here. I can calculate the amount of area that I will need to realize the heat exchange, and it will allow me to calculate the T out that I will have here and the T in that I will have here as a function of the area that I'm going to buy. Okay, now the question is, in fact, I still do not know what is the area, and I still do not know what is the heat exchange, the heat transfer coefficient. The heat transfer coefficient, I can find it in the literature. There are a lot of people who have been working on heat exchangers and who are giving you the value of the heat transfer coefficient. Okay? In order to make to have something which is easy to calculate or easy to handle in the case of the energy system integration, what we can do is, instead of looking at finding all the heat transfer coefficient and deducing the heat exchange area, so what we can do is to estimate a certain temperature difference that will be reached here, so at the place where we have the lowest temperature difference. And we will say, for example, that there will be 1 or 1.5 degrees C between the streams that is leaving and the stream that is entering. Okay? So we make an assumption, 1.5, okay? And it means that as soon as I have this value, I'm able to calculate the product of U and A here. Okay, because I can apply the energy balance on both sides, and I can calculate the heat transfer that is explained here. Okay, so this is the equation of the heat transfer. And as soon as I have the value of the temperature difference, I will be able to calculate the outside the exit temperature of the hot stream from the heat exchanger. Okay? But something which is even more interesting is that for any temperature outside, I will be able to calculate what is the exit temperature, because this equation is always valid. Okay? This will be considered as being a constant. Okay? So it means that for any outside temperature, so the Tx that is here, now I will be able to calculate what will be the Tin that my heat recovery exchanger will calculate, will obtain. Okay? Knowing this, I will be able to come to this equation here that I have just slightly modified, because now I have to realize that only part of the air is coming from outside. So it's the part that is entering by infiltration. And this air needs to be heated from the external temperature to the comfort temperature. And the part of the air that has entered into the heat recovery heat exchanger, right, is going to be, needs to be heated from the outlet of the heat exchanger, and I have given you the formula that allows you to calculate the outlet of the heat exchanger, right? And the comfort temperature that needs to be, that is asked in the room. Okay? Conclusion? By, on the one hand, looking at the recommendation of Minergie or other standards, I'm able to calculate the new heat transfer coefficient that I will then apply if I'm renovating the building. By assuming a certain amount of infiltration, a fraction of infiltration air, and by assuming a certain value for the delta T minimum in given external conditions at a given temperature that I have selected, I will be able to calculate as well the impact of the new heat load that is needed and the heat load profile that is needed by the building if I'm controlling the reusing the heat from the extracted air to preheat the air. Okay? And I will be able to calculate what is the area of the heat recovery heat exchanger that I have to buy in order to realize this operation. Right? Okay? So, what we have made by doing this is transforming an idea into something that can be evaluated and that translates into a profile of heat load that is needed by the system. Okay? And the heat load profile, so as a function of the temperature outside. Okay? And something that I have indeed used, which is the trick, is that at the end I do not need a lot of information. I have used the standard to know what is the target energy demand that will define, for example, the Minergie. I have used the standard to define what is the flow that needs to be renewed of air. I have used a rule of thumb that allows me to know what is the ratio between the inlet flow and the outlet flow. Okay? And I have used another rule of thumb that says, okay, typically the people consider that when the temperature is -10, for example, the temperature difference of the heat recovery heat exchanger will be 1 or 2. Okay, so a very limited number of information that is needed in order to assess different options to renew the building. Okay, and to calculate, to make the calculation of the profile. And something which is important here is that I have the max value, the max function here, which means that it will also consider the fact that you have optimized the profile of usage, okay, which appears to be here, okay, and that at a certain time the inlet flow is going to be heated by the gains inside the building. Okay? And of course, if I have heat sources that are coming from other sources, like like in a data center, okay? The only thing that I will have to verify is the compatibility between the heat source. So this is the heat source that is made available. That is, for example, the air that needs to be cooled down from the air cooling system. So the data center is going to give me hot air, let's say air at 50 degrees C, which is at 50 degrees C, and it is going to ask me to send back the heat at, let's say, 30 degrees C. Okay, and those are the conditions from that characterize the heat source. Okay, there will be something that I will have to do then is to identify what can be heated with this heat source. And then it appears that I can perhaps decide to heat the distribution system, or perhaps to heat the air, or to release the energy to the environment, depending on how the balance will be. Okay? So what it means is that I will have to be smart to identify what is the heat that can be directly recovered. Okay, so for example, the heat of the hot source that can be recovered in the distribution system. Okay? And afterwards I can perhaps also say, okay, but this one can also be used in a heat pump. Heat pump. Which means that as soon as I buy the heat exchanger that is here, so this will be a heat exchanger, then I will have to buy something which is more complex, because I will have to buy a heat exchanger here that is going to cool down the air, because this is a need, so it's a waste heat, but it's a need. Okay, I need to cool this stream, and I will use a heat pump that will use electricity to produce hot water, for example. But in this case, I will have to buy a heat exchanger to take the heat. I will have to buy a new heat exchanger that is going to send back the heat at a higher temperature, and that is going to heat up my heating system. Okay? So it means that now the heat recovery will be just a little bit more sophisticated, because then I will need to buy not only heat exchangers, but I will have to buy a heat pump that has the right size after I have bought the heat exchanger. Okay? And this will be the role of doing of using an optimization method to define what is the best size of this heat exchanger here, and what is the best size of the heat pump that needs to be installed here. Right? So it's just a question of being then smart in looking at the way we can recover heat in with waste heat that is available. I will use exactly the same principles. Okay, I will use the same principles because I will calculate heat exchangers here. So there will be somewhere an equation that is going to tell me that the heat exchange area is related to the delta TLM. Okay. Same method as before. That I will as well calculate as a function of the temperatures that are available, okay, and the variations of those temperatures and flows, okay. And there will be something which is even more interesting. There is that I will have to know what are the temperatures that are needed by the heating system, okay. And this is what I'm going to explain just after the break. Do you have questions? No questions? Then we do 15-minute breaks, and then I'm going to start again. If you need to know what are the temperatures here and here that are needed by the heat distribution system, which is indeed the temperature that is needed by the radiators when the valve is 100% open, okay? Then it means that I have to know what are those temperatures. So what I'm going to explain you now is how we can estimate the temperature at which we have to supply the heat in the building, okay? And for doing this, what I'm going to do is that I'm going to represent, I'm going to model a radiator. So a radiator is equivalent to a heat exchanger, except that the whole volume here will be heated, and yes, there will be a temperature difference of the air that is going to be heated. But what I can do is to make the assumption that there is a big volume at a constant temperature here, which is mixed by the flow of air. Okay, which is the temperature that the radiator is going to see. So it means that on the one hand, I will have a flow of water that is going to enter and that is going to leave. It is going to do the heat exchange here, okay, and that is going to see the temperature of the room. Which means that now I can represent, on the one hand, the heat that is supplied, which is in fact the heat that is delivered here by the water that is circulating at a given flow in the radiator, okay, and that is going to make a temperature difference. So I'm obtaining, therefore, the amount of heat that is delivered by the radiators in the room, and by extension in the building, if I'm assuming that the building is at constant temperature or needs to be at a given constant temperature. Okay, so now I have the heat load that is needed, that is supplied by the water with a given flow of water and two temperatures. This heat load is also following the heat exchange formula. Okay, so it means the principle of the heat transfer, which is expressed by the logarithmic mean temperature of the heat exchange, which is shown here. Okay, so this is the delta T Lm, in which you can see that there is a constant value here, which is the comfort temperature, which is not changing, while you have the inlet and the outlet conditions of the water. And here I'm making the assumption that it follows some sort the countercurrent principle. Okay. So, what does it mean? It means that if I know the heat load that needs to be supplied, because this is something that I have calculated, because I want to maintain the temperature at the comfort temperature that I need, which is coming from my previous calculations, and that depends on the renovation of the air control, etc. Okay, I know the heat load to be supplied. If I know the flow in the circulating pump that is sending the water in the system. I will, and if I'm considering that the heat transfer coefficient in the area of the heat exchanger is fixed, and this is a reality, the heat exchanger has a given heat exchange area, then I will have two equations, this one, in which, and this one, in which there are two unknowns, the inlet conditions and the outlet conditions of the water. Okay? So it means that with those, by using those two equations, so the first thing that I will do is that I will replace, using this equation, I'm going to calculate the T out, which is equal to QBT, so at a given temperature, divided by MCP, and everything is known, huh? Plus, it's T in minus QBT. Huh? Okay, so I will have T out, and then I can add T out here, replace T out everywhere, and then solve this equation. Okay, so as you have passed the first year in EPFL, I will let you find the solution because there is an analytic solution to this equation. So this equation, if I'm replacing T out by the function that I have here, which is a function of QBT and T in, okay, I will be able to calculate, as soon as I have the UA, I will be able to calculate the T in as a function of for a given flow of water, which is and values of U and A. And you will have to make the calculations. Something that I can tell you is that the results that you will obtain will be something like this, where you have, for different value of QBT, you will have different values, which are the limit of the temperatures that the heat distribution system needs to have in order to use the heat exchange area of the radiators. Okay, so it's the lowest possible temperature because it means it makes the assumption that the valves are fully open. Okay, but the trick is that now I have a formula that is going to give me, as a function of the heat load that is needed by the building, what are the temperatures at which the heat needs to be supplied. Okay? And I would then ask you to make the calculations, and there is a trick here that I will use, is that typically we give you a value, which is saying that when the temperature outside is, for example, minus 15, this is the typical typical temperature here, the system has been designed to operate at a given temperature. So, and I have given you the temperatures of the high temperature distribution system and the low temperature distribution system. Okay? You have to consider that those values are the ones that are for the extreme conditions, so for minus 15. Okay? So it means that you know T in and T out for one condition, the maximum heat load to be supplied. Now, what you are going to do is that you are going to take the maximum heat load that you know. You are going to take the T in and T out that are characterizing the heat distribution system, and this is given, so you know T in and T out. And as you know T in and T out, and you know the heat load, by the energy balance here, you will be able to calculate the flow times the CP, and by the heat transfer equations, you will be able to calculate the value of UA. Okay, so in summary, for extreme conditions, you will calculate QB at minus 15. From the energy balance, you have the M water times the CP of water that is equal to QB divided by T in minus T out. And you will say UA is equal to QB divided by the delta T LM for T in and T out. So now I have UA, I have MCP, so that I can then calculate the two curves that are here as a function of the heat to be supplied.
The
Yeah.
T comfort is known.
T comfort is known, so you take 21 degrees C, and this is something which is a set point that has been used for the design. Okay? So, what does it mean? It means that now I have not only the possibility of calculating how much heat needs to be supplied, but also at which temperature the heat needs to be supplied. Okay? Which then allows me to go to the energy conversion system. So what will be the electricity consumed by the heat pump that needs to be supplied a given temperature from a given source? So you remember that, I hope that you remember what is a heat pump. Yes? So a heat pump, so it's a key technology for heating purposes. Okay? A heat pump is going to use a heat source at a low temperature, and it is going to use the heat source, for which I have the inlet and the outlet conditions here, to evaporate. So this will be an evaporator. At low pressure and low temperature, that is going to receive the heat from the heat source to make the evaporation. So here I will have a vapor stream that is produced. This vapor will be compressed by the help of an electrical motor. I'm going to consume electricity, and I'm going to go to high pressure and therefore high temperature. And I'm going to use this compressed high pressure stream, which is also in a vapor state. And I'm going to condense it into a condenser. Condenser. So the condenser is not a condensator. Okay, so that's for the electricians here, so that's something different. So a condenser is a heat exchanger in which a fluid is going to go from the vapor state to the liquid state. Okay, and here we consider that we are just at the saturation. Okay, and going from the vapor state to the liquid state is going to deliver heat, and this heat will be used in order to supply the temperatures and, in fact, the flow that is needed. So it allows me then to know what is the heat that is delivered by the condenser of the heat pump. Once the heat is delivered and that I've reached the liquid state at high pressure here, then the heat pump has the next element in the device, which is a valve that is going to allow to expand from the high pressure here to the low pressure here. And here typically I will have a liquid vapor state. So it means by doing the expansion, part of the liquid is going to pass to the gas state. But not all. Which means that I will need to have, if I want to have a full vapor state here, I will need to supply heat to make the evaporation again. But it's at low temperature, okay? And this is the benefit, okay? So if I'm writing the energy balance, I know that the heat that is supplied by the heat pump, so the QH minus that is expressed here, is equal to the heat that is taken from the heat source, so this one here, okay, plus the energy that I have added in the heat pump. Okay, so this is the energy balance of the heat pump. In addition, I know that the heat pump is characterized with a COP, coefficient of performance, which is the ratio between the heat supplied and the electricity consumed. So the better the COP, the higher the value, the less electricity you need in order to supply the heat. Okay? And if you look at the equation just above, it means the more you take heat in the heat source at lower temperature. Okay? The theory of thermodynamics is telling us that the COP can be estimated by saying that by looking at the maximum value that the COP can reach. And the maximum value that the COP can reach is coming from the Carnot formula, and is expressed here, in which I have used mean values in Kelvin, okay, of the heat source and the heat sink. And the mean value is in fact a logarithmic mean value. So it's, as it is shown here, so the logarithmic mean value for the heat sink is the inlet conditions minus the temperature of the inlet conditions minus the temperature, the outlet conditions, so of the same source, the hot water that is produced, for example, divided by the logarithm of the ratio of the inlet and the outlet conditions. Okay, so the temperature of the heat of the heat source, the heat sink here, is based on the mean value between those two temperatures here. Okay, in Kelvin, please. It's thermodynamics. And what we know is that the real COP is always a fraction of the theoretical value. I cannot be made better than the theoretical value, but in this case it would mean that I would have everything that would be reversible, so it means that there will be no friction in compressors, so no transformation of any form of energy into heat, okay, which is impossible because it needs things that are done very slowly and would require heat exchangers with infinite area. Okay? So it means that this is not what we are interested in. But what I can tell you is that typically here the fraction of the maximum value is, by the knowledge of engineers today, of the order of magnitude of 55%. Okay? There is something which is very interesting by using this, by knowing that we can reach the 55%. Is that now I can calculate the COP of the heat pump by just looking at the temperatures at which the heat is needed and at which the heat is available. Okay? I can apply this formula here. I have the mean values of the heat source. I have the mean value for the heat sink. Okay? And I know that typically I will be able to find on the market a heat pump that will consume this amount of electricity that is calculated by the COP that is here. Okay? Advantage is that I have not made any thermodynamic calculations of the fluid, so I do not have to make a calculations of what is the pressure and the temperature and the enthalpy and the entropy here. I do not have to account for any compression calculations, but I have a good guess. Okay? And it is based on temperatures that I know, because I have made all the calculations to know all the temperatures. Okay? So it means that now I will be in a position of calculating the amount of electricity that is needed by any heat pump that is supplying the heat to the temperatures that I have calculated, to any of the buildings that I have calculated, or perhaps renovated. Okay. I don't know why. Let's do this. I'm going to change. Okay. Okay, and I have the value for any time. Okay, depending on the temperatures that I have calculated. So now I have a good estimation of what will be the amount of electricity that is needed by any heat pump that I'm going to integrate in my system. Okay? So everyone is therefore happy, right? Because now I know how to heat my building, and I will be able to make the integral knowing the amount of heat that is needed, knowing the temperatures that are needed, knowing therefore the amount of electricity that will be consumed by the heat pumps. And as you will be very smart, you will say, well, I have an electricity consumption. So why don't we use PV panels to produce this electricity, so that only part of the electricity needs to be imported. The rest can directly be produced from the PV panels that I will have on my roofs. Now the question is, how do we calculate the amount of electricity that is produced by the PV panels? Now what I know is the amount of area that I have on the roofs. Oops, I don't know why he's... Okay, so we know the area that we have. So now the question is, how do we calculate the electricity? And the electricity that we are going to calculate depends on the irradiation that we have on our roof and on the efficiency of the PV panel that we are going to use. Okay? So it means that I will be able, therefore, to calculate the amount of electricity produced if I know the area, and means I have to look on the roof, and if I know the irradiations times the efficiency of the PV panel. And to identify this value, you are lucky because there are tools that allow us to do it. One tool is PVGIS, and you have so you can look on the internet and type PVGIS, and then you will have access to the amount of electricity that can be produced by a PV panel. You can even optimize the orientation of the panels so that they are well positioned with respect to the course of the sun. Okay, and there is another one today. So it's a new system. The name is toitsolaire.ch. And if you look at toitsolaire.ch, you will see you type the address of the building, and it will give you the amount of electricity that can be produced on the roofs. It takes into account even the shadings. Okay? And it is even going to give you an estimation of how much it will cost. Right? So now, indeed, I'm quite happy because I have everything that allows me to characterize the buildings. Okay? And even the energy consumption that is needed by the buildings. That's what you will have to do now. So different options of renovation, different amount of PV panels on the roofs, and the possibility of calculating how much a heat pump will consume. Okay? you have questions?